it's great to be here. So I'll be talking with Nicolas about distributed randomness. This is a project that kind of started quite a number of years ago. Motivated from various contexts. Nicolas, just to introduce Nicolas briefly, he was a member of the DEDIS lab for several years, in particular when the Drand project was really getting launched, and he's continuing to work on it in the context of protocol labs. And so I will be doing the first part of of this talk, and he'll focusing more on the research stage of this project, and Nicolas will take over later for the more deployment focused on the latest stage, the Drand and League of Entropy. So just to introduce my lab briefly, I often say, my lab is not a blockchain lab by any means. It's a decentralized and distributed systems lab. And it's basically motivated by my perception that so much of our computing infrastructure is based on what I consider weakest link security. And this weakest link security just gets worse as things get bigger and more complex and more participants and stuff like that, because there's greater and greater chance of any weak link breaking. And the grand challenge of the lab that I've been that's underlies most of my lab's work is trying to figure out how to re-architect systems to turn it around into strongest link security, security and privacy that gets stronger as the size, complexity, number of participants, etc. increases. And of course, this is at the heart of our distributed randomness work, along with many others. And part of this is how to make that strongest link security scale. How do you make it so it works not among just 5 or 10 nodes, but 100 or 1,000. And so we'll come back to that later. So this is a current snapshot of my lab. Obviously, many others have been in the lab before and will be in the future. And this what we'll be talking about is the work of many people. So a brief outline of the talk. First of all, I want to briefly introduce the public randomness topic itself. Why do we need public randomness? What are the challenges? And then I'm happy to say that to see that Andrew actually already introduced MPC in a more general fashion, but I'll go back to introducing Shamir secret sharing, which is a very fundamental piece of what these randomness protocols depend on. And then just very briefly, and then get into 2 of the research protocols that we developed at the DEDIS lab, and then Nicolas will cover the League of Entropy and the deployment DRAND protocol. Okay, so let's first of all look at public randomness. Why? What is it? So the need and applications and uses of public randomness has been around for a long time. This is kind of a very old tradition coming from lotteries, even the tradition of people flipping a coin, heads heads or tails, who wins, some bet or some whatever. Heads, I wash the dishes, tails, you wash the dishes, that kind of thing, right? This is all public randomness, where you want the outcome to be random, so nobody can predict it, but public. You're not creating a secret key or something. You're creating randomness in public. You want it to be trustworthy and random, but it doesn't need to be secret, and you don't want it to be secret, right? Of course, historically, there are often many ways and instances in which this has gone wrong, including randomness generated in completely non-technical fashion. Like there was this incident where it was claimed, I'm not sure if it's actually true, that the FIFA, lottery was hacked by warming up some of the balls and cooling down the others, so that the person who reaches in the bin to pick a ball knows, which balls to pick up and which not to, right? That's Whether or not that actually happened, it's one of the many ways that supposedly public randomness can be hacked, right? So let's look at public randomness in the actual computer science or blockchain context. So there's many purposes and uses of public randomness. So obviously choosing a lottery winner, creating input to games that, randomness-based games, sorting card decks and things that you want to make sure are fair and unbiased. Things like fair sampling, picking a sample of a larger population, a population of people, or for example, a population of stake in a proof of stake system. There's a lot of reasons we need samples, and often security depends on those samples being fair. How do you ensure that they're fair and unbiased? Things like scalability of mechanisms like sharding, which DEDIS lab, the DEDIS lab explored quite a bit in our OmniLedger project. And many other classic distributed systems have depended on picking a sample or quorum or something like that fairly in various ways. So there are a lot of reasons we need public randomness, but now what can go wrong? Once again, it's important to distinguish public from private randomness and keep track of which we want at a given time. So one of the common mistakes have been made has been mixing that up in some way. For example, using a public randomness source to generate your private RSA keys or something is a really bad idea, but that should be obvious. But unfortunately, a lot of people have done that kind of thing, right? But similarly, using private randomness, in some code that's trying to generate a public, value of some kind, has also been a big problem. Like, for example, the Swiss e-voting system got in trouble lately for kind of having a newbie crypto bug where the source of what should have been public randomness was used private randomness, which basically anybody running the server could hack to completely break the system. So getting the difference between public and private randomness and how you generate them is very important. Of course, there's other things that can go wrong, like just using low quality or low entropy random generators or sources. This is why modern processor hardware generally has random numbers generators built into the hardware. It's really hard to do to generate true good high entropy randomness purely in software with limited sources and unreliable sources of entropy. But that's also not the main focus of this talk. The main focus of this talk is how do we get trustworthiness for public randomness? Regardless of the quality, just assume you've got high enough access to high enough quality randomness, which is generally true if you don't have a serious bug. But do you trust who flips the coins? And should you trust them? And even if what comes out of a series of coin flips looks random, and even if you're convinced it is random, is it truly uniform? And if it's even a little bit non-uniform, lots of really bad things can happen in the crypto and blockchain world. I won't get into the details there, but we'll come back to that topic later of bias. So of course, as you might expect, there's a lot of ways to generate randomness. So the approach we'll be talking about here is most similar to some work Christian Cachin and others did way back in 2000, and it started even earlier, but this was one of the real representative early works along this line, using secret sharing for randomness. But there's other approaches, kind of pure crypto approaches, by like using computationally hard, slow hashes to generate a randomness in a way that you hope it'll take anybody a particular amount of time and effort to generate or check the random number. So this is also something we're not going to talk about. You can also just monitor existing proof of work blockchains like Bitcoin and get randomness of a certain quality. And you can evaluate, how good a randomness, how bias resistant it is, how much, namely, how much it would cost to break or to bias. And that's a different, very interesting approach. But so basically the focus of this talk will be the T of N threshold model, just like in the MTC world that Andrew was talking about. Where you assume that somehow you have a group of N nodes, and you're willing to assume that fewer than T of them will be compromised and colluding together, right? And so this is a very natural and reasonable assumption for permission systems. It can also work in open systems with techniques such as mechanisms to automatically elect groups, like Bitcoin and Algorand do. Of course, it has incentive compatibility issues, like Andrew was talking about. How do you know if T nodes are colluding? Can you hold them accountable? And I won't be trying to solve that problem. But so the upshot is the solution space we'll be talking about applies to this T of N threshold security model. Okay, so that's the basic background. Now let's switch into a brief overview of Shamir secret sharing for anyone who is not already familiar with the concept. I'm not going into any detail. You'll find plenty of technical details in all kinds of tutorials and Wikipedia, etc. if you want. But this is the way, basically what Shamir secret sharing is. It's a foundation of most threshold cryptography, including threshold encryption, threshold signing, general multi-party computation, and it's really decades old. But Bitcoin and most existing blockchain deployed systems don't seem to use it much. Some of them are starting to. Some of the more cryptographically advanced ones definitely are starting to, but it was definitely slower catching on than concepts like hashes and zero-knowledge proofs. So what is Shamir secret sharing? Well, the basic concept is assume you have some party who has a secret and wants to deal it out, make shares of it, namely make N shares of it, such that any T parties, where T is less than or equal to N, any T parties can cooperatively recover or cooperate to use it in some way. But if fewer than T parties try to do anything with it, such as because they're a colluding attacker, colluding with an attacker, no sub-threshold set of parties can do anything or learn any information about the secret, right? So how does this work? Now, just to illustrate the math behind it in a very basic fashion that I try to use to explain this, suppose you're a pirate. You've gotten some booty, and you want to bury your treasure and go back for it later. How do you keep the treasure secret? Well, you find a place to bury it and make a map with X marking the spot. Of course, that's what you do. You're a pirate. But you're a lazy pirate. You don't want to go back to your buried treasure. You want to send your henchmen to go back for you. And it so happens you have 3 henchmen that you want to send back, but you don't trust any one of them completely. But you also recognize that one of them might get sick and die, or get shot in a barroom fight, or something like that. So you don't want all 3 of them to have to go back. So you want any 2 of the 3 to be able to go back and get it for you, but you don't want just one who might defect to be able to find the secret. So how do you do this? Well, here's one way to do it. You find 2 reference points with the X on the line between them. You draw that line on the map, and then you find some reference points to draw 3 more lines, so approximately parallel to it, right? You draw another line that intersects all of the existing lines, and you, at exactly the intersections, mark 3 X's. Now, the positions of those X's are your secret shares. You make 3 more maps to give to each of your 3 henchmen, each map showing only one of those secret share X's, right? So if you think of it very, very simply, you'll see that with just one of those secret share maps, you know, that if one of the henchmen goes back to find your treasure, they won't be able to. But any 2 henchmen will be able to, right? So the one defecting henchman who's trying to go back with his map, he has only 1 X, and he can draw an infinite number of lines through that X, and he won't have any idea where the secret actually is. But if you have any 2 henchmen working together, they can draw a line through their 2 X's and find exactly where the secret is, right? So very simple, but very beautiful, and works great. Of course, the threshold doesn't have to be 2. The threshold can be any number. So if you use a bigger number, you just need to use a higher degree polynomial. So so if you want a threshold of 3, you use a degree 2 quadratic polynomial, and so on, right? So it just works. Now, of course, making this really work in real systems had a lot of details that I'm not even going to touch on here. So, you know, there's a lot of materials out there. So let's instead, you know, with that brief introduction, let's go back to the topic of randomness. Why does randomness need or want secret sharing, and how do we use it? So we're going to dive into the research protocols that DEDIS developed. Now, like I said, threshold distributed randomness are not new. They've been around for quite a few years, but it's also well known that unfortunately secret sharing can be both expensive and hard to scale, both in a computation and a communication sense. For starters, you need some kind of setup protocol to generate and distribute the keys. That comes with cost and complexity. But even once things are set up, the typical naive standard ways to build these protocols usually give you at least order n squared communication cost and order n cubed computation cost, even after setup. And so they're not that, and you know, where n is the number of participants. So they're not that scalable by default to large numbers of participants, right? So this scalability problem was really what we were trying to focus on in developing the RandHound and RandHerd protocols in this paper in IEEE in Oakland 2017. Basically, we wanted to say, okay, suppose we have a standard T of n threshold model, but we want it to really scale. So we want it to scale so that hundreds or thousands of nodes could participate in it directly, like either a really big federation or perhaps a large automatically chosen group out of a proof of work or proof of stake based system using, Bitcoin or Algorand-like techniques. So, without getting into that, basically that's the motivation. And generally, from the argument that if you can really increase n to hundreds or thousands, and the other aspects of your system are reasonable, you can really hopefully diminish to the probability that the system can be compromised to be, ludicrously small, practically negligible. So that was the scalability goal. So scale to large numbers of participants, or as large as needed. So what makes this hard? So to illustrate that, let's first look at a couple strawman examples to see what goes wrong. Let's start with the naive, kind of the easy, naive way of creating distributed randomness, which at first might seem pretty pretty decent. So let's say you've got n nodes. You don't want to trust any of the n nodes, for the randomness. Any of them might be colluding to bias or leak the secret. So you have each of the n nodes pick and commit to a secret. send all the others a hash or some other cryptographic commit to the secret that they're not going to be changed. And then, have everybody wait to get everybody else's secret. And then everybody reveals their secrets that they committed to earlier, right? And there has to be a barrier between those two phases so that everybody reveals their secrets after they know everybody else has committed to them, right? And then once you do that, assuming everyone shows up and does what they're supposed to, they can only reveal one output. And as long as there's at least one honest node that didn't leak their committed secret to the adversary before going through this process, you're going to have good randomness. You're going to combine all the revealed secrets together, and nobody's going to be able to predict or hopefully bias what that was, right? So sounds attractive, right? But in practice, it totally doesn't work, and that's because what the basic problem is, what if not everybody shows up? What if not everyone actually reveals the secret that they committed to? So what if some people participate in the first phase, but then disappear for whatever reason before the second phase and just fail to reveal what they committed to? Now, you can say that, well, the protocol fails in that case, in which case you didn't get your randomness, right? And that's a big denial of service attack, letting one node that doesn't like the output, hold the whole group hostage, is a huge denial of service attack. If you try to repeat the whole process, then that's a huge bias attack, because any node, that doesn't like any node can say, wait for all the other nodes to reveal their output first, see what the output would be with their private secret. And if I don't like the outcome, well, I'm gonna just, pretend I went offline and hope everybody does it again, and wait till I get an answer I like better. So that's a huge bias attack. Now, of course, you could try to make this scheme more resistant to denial of service by saying, okay, we're only going to require T, some threshold T out of the N nodes to show up. That way we can tolerate N minus T nodes disappearing in phase 2, right? So that would be nice from a DOS protection case. But now the problem is we get to phase 2, and there's up to up to N minus T of these nodes that haven't shown up. Well, we are missing the secrets that they had committed to that are supposed to get mixed in to produce that randomness, right? And so any way we can choose to combine the remaining revealed secrets is going to depend on which specific set of nodes did and didn't proceed to phase 2, right? So the way you combine them has to be a deterministic function that everybody can agree on, so everybody can verify the output. But this means there's basically an exponential bias risk, right? So if some attacker controls some number F of nodes, then those malicious nodes can basically wait for all the honest nodes, participate in phase 1, and then wait for all the honest nodes to reveal their secrets in phase 2, and then the attacker can compute every possible output for up to two to the F possible outcomes based on whether each of the F attack nodes stays in, reveals their secrets, or drops out and refuses to reveal their secrets, right? So that's a 2 to the F exponential bias vulnerability if you let that happen. And almost needless to say, that bias vulnerability gets exponentially worse as the group gets larger. If N is only 3 or 4 or 5, then maybe this isn't a huge bias vulnerability. If N is 100 or 1,000 and F is supposed to be a third or a half of that, then that's an enormous bias vulnerability, right? So that doesn't really work. And so this is why we need secret sharing to do threshold randomness like this well, right? So of course, the basic secret sharing mechanism assumes there is a dealer with a secret, but we don't want to trust any single node to choose the secret for anyone, because we don't want to trust any single node with the randomness that we're generating. And so instead, we treat everyone as a dealer. We say, okay, all n nodes are each going to deal a secret to all the other nodes. And in this set of deals, they're basically producing a big matrix, as you can see on this slide. And fortunately, secret sharing is a nice linear process, which means all these nodes can commit to the random polynomials they're producing to deal their individual secrets. And we can add those polynomials and those commits together, basically homomorphically, without getting into the details. And that basically produces a secret sharing polynomial that everybody knows, everybody can agree on, but nobody knows in advance what secret it actually represents. So this produces the joint threshold secret, right? And so that's phase two. Phase one produces this matrix. And then in phase two, all of the honest nodes, or at least T of the nodes, go and reveal their shares of those secrets, with the knowledge that as long as at least T nodes remain live and reveal the shares that they the correct shares, there's various ways to hold them to this promise. Then we will be able to reveal the secret, even if and it will always be the same secret, regardless of which set of T nodes. So and so the secret that gets revealed will not have any chance of being biased by which set of F nodes might drop out at the worst time. So that it completely eliminates the adversary's 2 to the F bias vulnerability, right? So problem solved, right? So that's great. And it's worked, and it totally works, but again, coming back to the scalability issue, it's still typically, the obvious ways to do this typically have n squared communication, n cubed compute. And so the next question we asked is, can we make this scale better? Now, if you're familiar with our lab's OmniLedger protocol, which is basically sharding, you're probably already familiar with this concept. And there's many cases where sharding is useful, basically taking a large group of participants and picking a smaller group as a sample of the larger group. A very powerful technique. And RandHerd and RandHound came before OmniLedger. They were, in fact, partly motivated by the need for distributed randomness for OmniLedger, right? So these were tools we built on the way to OmniLedger. And so RandHound and RandHerd are basically trying to scale distributed threshold randomness to very large scales. But this is hard, partly because we want to use sharding, but we run into kind of a chicken and egg problem. We know that if we can break one giant secret sharing group into many smaller ones, we can definitely make secret sharing scale better. But to do that breaking up or picking the groups, we need public randomness, to make it secure and unbiasable. But to get that randomness, we need we need this protocol, and we don't have it yet, right? So it's a real chicken and egg problem. So I won't get into the details, but the intuition of how we solve this is basically in 2 steps. RandHound is the first step. And basically what RandHound does is it's a client or initiator driven protocol where we assume that somebody, couldn't be anyone, a client wants randomness. Now, and we're going to assume, in this protocol that the initiator, whoever that is, wants the randomness, and we're going to trust that initiator for liveness. If the initiator doesn't complete the protocol, then the initiator doesn't get the randomness they wanted, and that's not our problem, right? That's the initiator's problem. So, but we don't want, so in a sense, we're willing to trust the initiator for liveness to complete the protocol if it wants to the protocol to complete, but we do not want to trust the initiator for honesty or integrity. So we don't want the initiator to be able to bias the randomness. And to make this work, we have to guarantee that in any given protocol run, the initiator has to get only one try to produce an output, right? Because if the initiator can just rerun the protocol many times and pick the output it likes best, then that's going to be biasable, right? So the basic premise is the initiator has to say, okay, I'm starting this protocol, I'm going to try to finish it, and the only two outcomes are I failed to finish it, or or it did complete, I did manage to complete it, and here's a random output that everybody can trust to be truly random and unbiased and unknown to anyone, including me beforehand, right? So without getting into the technical details, the basic idea is we can allow the initiator to use private randomness to pick the shards or subgroups. So the initiator is solely responsible for taking 100 or 1,000 participants and breaking it into smaller groups of 10 or 20, right? Now the initiator can do a good job of that or bad job of that, but the way we set it up, if the initiator does a good job, then the initiator can guarantee with high probability that the protocol, that they will be able to complete the protocol. Now, if the initiator does a bad job of picking these subgroups and uses bad randomness, which the initiator can totally do. He can pack his henchmen into one subgroup. But the worst he can do by doing that is shoot himself in the foot. He can pack, say, nodes that are going to make the protocol run fail into a group. But he can't pack, there's no way, basically by application of a pigeonhole principle, we guarantee that there will exist at least one subgroup that will maintain the integrity of the system, no matter how the initiator, the malicious initiator's henchmen are packed into groups. There has to be one good subgroup, and the initiator is forced to use the output of all the subgroups to produce the final randomness, including the one good subgroup that has to exist by the pigeonhole principle. And therefore, the only thing the initiator can do by using bad randomness for its sharding is to shoot itself in the foot and make it harder or impossible for itself to complete the protocol, right? So that's RandHerd. Now, it's not where we want. Where we really want to go is to get something we call a randomness beacon, something that kind of acts as a virtual trusted third party that just generates randomness on its own without depending on any single leader or initiator to do its job. Now, of course, there's a bunch of challenges in making this work as well, but just to get the high level intuition, we basically use, we form OmniLedger style shards, but we use RandHound to bootstrap these shards. We say, okay, we're going to use, in this case, PBFT style leader election in a consensus protocol, but to decide what, how we're going to shard this system and how to set it up. But as part of that, whatever leader is running that protocol at the moment is going to use RandHound to try to set up its view. It has to use RandHound because all of the honest nodes will not accept a new view unless RandHound has been used to produce randomness that's good, provided the leader carries through its view change around, right? So if the leader behaves well and executes RandHound to completion, it gets a new view set up with appropriate sharding that everybody can depend on it to be truly random. If the leader fails in its duty and doesn't run RandHound completion or fails in any other way, then, oh, well, it just loses the view leadership, and eventually another view leader gets a chance to try to set up a new view, right? And so basically this bootstraps a sharded system in which each of the individual groups is guaranteed to be random, not under the control of any particular leader, but under control of good public randomness, that can then basically operate autonomously and generate threshold randomness in a way that doesn't depend on any particular node or any sub-threshold number of nodes. Okay, so that's all I'm gonna say about those two protocols so far. The main point, the final point is simply that it works. If you want really scalable randomness, then RandHound is your friend. It will, we showed how PVSS, publicly verifiable secret sharing, which is the simple classic way of producing threshold randomness, it scales to some degree, but even when you get to 256 or 512 nodes, you really start to see the quadratic costs, and it's still, each round starts taking many seconds or minutes, whereas RandHerd takes only a couple seconds to complete a round, even all the way out to over 1,000 nodes, and that's where our test bed ran out of steam. So we know it can scale a lot more than that if you need to, but that's how far we tested it. Okay, so that's how we came up with protocols that we're very confident, we can scale. They work, they generate strong public randomness, and they can scale however much we need. On the other hand, in an immediately practical protocol, if we want to get, deliver strong public decentralized randomness to the world right now, well, it's definitely going to be a while before we find, hundreds or thousands of independent people or organizations willing to run RandHound or RandHerd nodes, right? So at least in the short term, we actually don't need the scalability that RandHound and RandHerd provide. And instead, a lot of other engineering and other simplicity issues come into play. So RandHound and RandHerd are not the best protocols for actual practical deployment at least in the near future, right? And so that's what motivated and really launched the DRand project. And this is where my colleague Nicolas will take over, since he really initiated that and led it into the current state of actual deployment. And so Nicolas, are you ready to take over?
Yeah, I'm ready. I will share my screen.
Nicolas, I can't hear you. Can you hear me? Yeah, so Nicolas,
sounds good.
I will take over the screen sharing. Good, thank you. I can hear you. Yeah, thanks. Take it away.
Okay. Hi, everybody. So there's definitely some challenges into deploying such system. So there's like as you all know, distributed system is hard for plenty of reasons, for debugging, for testing, for implementing. And in particular, this protocol, there's some hidden uncertainties, like some at the view change, which is how do you change leader when the leader is malicious, for example, is not trivial at all. In particular, the communication trees, also how to make them scale, and what happens when there's a failure in one of the trees is not a trivial subject at all. And there's like also what happens when there's some malicious participants who need to reconstruct this private key, which is also induce some delay. So there's like different aspects in terms of deployment, in terms of practicality, in terms of robustness that are present in this system as well. And I want to present you another, let's say, a next a simplification of randomness protocol that relies on different assumptions that has been and it's been inspired from Diffinity's network for those who know what it is. So at the basis of Drand, we have the distributed key generation. So I won't go into too much detail because now in like 3 talks we've been talking about it, I think. But it's similar to RandHerd as an initial ceremony between nodes. The only difference is that we're not doing a publicly verifiable secret sharing, as this gives us a point in a curve. We are really doing a very verifiable secret sharing, but every node is doing this one. So at the end, we have a share of each node as a share of a secret and not a share of a point. So with this, you can enable distributed signature, distributed encryption, and many other things. And then once we have this, the set of nodes simply do partial signatures. So I'm going to explain what it is later on, and they broadcast these partial signatures, and everybody record these partial signatures and aggregate locally to generate this randomness. So let's see how that works. So the distributed key generation, I've already told you a little bit, so I'm going to quickly pass on it. So we just run. If we have n nodes, we're going to run n VSS at the same time, and in the end, you have multiple shares. You add them together. That's for the simple Peterson decay, let's say. So how do you actually generate randomness once we have these shares? Okay, so I'm going to need to introduce some notation about the pairings curve, which Mary already talked a little bit before. So this is like a special family of probability curves where we have this special mapping. And we have this key property of the mapping is we have G to 1 to the A, G2 to the B, and equals E to G1, G2 to AB. So in some sense, it allows us to solve the decision differential problem. It allows us to open greatly the possibilities what we can do. Its pairings is used in a lot of places in the blockchain space now, in zero knowledge proofs as well, in 16, etc. So how do we can use pairings to generate randomness? There is something which is called BLS signatures. So BLS signatures is a unique signature scheme. So compared to the regular Schnorr or ECDS, EDDSA, ECDSA for more precision, then that means for a given message, there's only one signature, and a given public key secret key pair, there's only one signature is possible. So it's very simple. You can see for signing, you just hash a message and you put to the power of your private key. And for verifying, you run this pairing equation to see if it matches. So VLS signature is very simple, then they use pairing. That's why we need there. And what can we do more with VLS signatures? We can threshold them. We can have the threshold version. So thanks to distributed key generation, we create a shared secret, and then now we can actually do a partial signature. So instead of hashing the secret and exponentiating with your private key, you will exponentiate it with your share that you get that you had during the distributed key generation. Finally, when you get T out of n of these shares, because you are doing a threshold distributed key generation, then you can locally aggregate to get the final signature. So aggregation is simply Lagrange interpolation, but you could run different aggregation. And it works out. In the end, you get a real BLS signatures as if you had the private key in a centralized fashion. So this is really the key aspect cryptography of Drand, and which have been explained before in the different talks. So if you have any question, let me know, but otherwise I'm going to a bit faster. So in Drand, we have this notion of chain of randomness. So basically every round, we're working around every 30 seconds for the current network, we are releasing a new randomness. And that means each node will partially sign the hash of the previous signatures and the round number. Actually, it's supposed to be I here, not I-1. And at each round, each node will collect all the partial signatures it can get, and any subset of T partial signatures, it will Lagrange interpolate, and it will do the final signatures. Then, if we want randomness out of that, we simply hash the output to get uniform, bitwise uniform distribution, because the signatures is still on the elliptic curve, and to get 256 bitwise uniform distribution, we still need to hash it. So one of the in order to deploy such system, we need to have the ability to not have a fixed set of nodes. That's important for many reasons, because if you fix a set of node at the beginning, you are let's say you need to make it evolve in case of node don't want to participate, in case there's no failure in a node, in case it becomes malicious, we know isn't being not trustworthy anymore. Also, in case of we just want to refresh the share. So like in any deployment, cryptographic deployment, it's never a good idea to keep your key around for many years. So we have this notion of resharing, where we allow the current network that is running Drand and running this generation to perform the resharing of their share to completely different, potentially different group, where we can change the number of nodes, we can change the threshold of nodes. And but the nice things about it is that we still keep the same distributed public key. So that means from a client's perspective, the client doesn't need to know about any change about the internal network of Drand. You can still give it a single public key and it will always be able to verify the new randomness generated by this new network. And this is really important in case you want to make practical application about it, because we ideally want to hide the complexity of deploying a new network and not having this key evolution, which is not totally practical, at least nowadays. It's coming, but it's still not, it's still hard. So with that, I just present you Drand. So we started this project a few years ago at DEDIS. I started this project at DEDIS. It was based on a collaboration with Dfinity. The goal of Drand is simply to generate randomness, but the only thing it does, it tries to do it well. There's no blockchain. Now it's on its own GitHub repo, and there's a team working at Protocol Labs on it since recently, because we're gonna deploy it in a, let's say, production-ready manner now. It's been launched last year more as an experiment project, which started quite well, and then now it's getting more serious. And the curve is BLS12-300-81. So it's the property of this code, the nice particularity of this code is it's being used in many different blockchain projects nowadays. So it's going to be compatible with Ethereum 2, Filecoin, and others blockchains. Just a quick slide on like deployment, because it's important to realize the difference between research. So I was both a research engineer and a PhD student at DEDIS, then moved on to more to industry, and it's important to realize the difference between research and the production-ready network. So you want to hide the fact that Drand nodes are actually running Drand. You want to protect them from DRS issues for increasing liability, for increasing the risk of hacking. So we want monitoring, we want firewall, IP whitelist, and we separated the distribution of the randomness from the creation of the randomness. So Drand nodes just create randomness and aggregate locally, and then they send this randomness to some distribution servers which are publicly exposed to the internet. So we have this two-layer approach here, and we have HTTP endpoints, and we have gossip sub or gossiping, which is used by Ethereum and Filecoin and many other blockchain to transact things. So this gave us to last year we launched the League of Entropy. It's becoming more and more larger. You can check the website here. We have a new website coming up just for this project, which is there's more news coming soon next week, but I cannot say anything today right now, unfortunately. So you have to wait for next week. But the basic idea is to be able to provide randomness for many services on the internet, as blockchain, as not blockchain as well. It's really, you can think of it like an NTP server deliver randomness. We want to run the NTP servers deliver times. We want to be able to deliver randomness with this type of service. So right now the members have grown quite a lot. It's not all members are currently running Drand. We are in discussion and we are testing phase with these numbers. You can see we have Cloudflare, EPFL, and so on. So it's growing more and more, and we have more partners on the waitlist. And the goal is to have a decentralized and diversified network. So we want diverse jurisdiction, we want diverse geographic localization to be able to raise the cost of attacking the network. Because obviously with threshold technology, if you get a threshold, things can go wrong. I want to note in particular that here, even for if you attacker get a threshold of keys. So we have the resharing mechanism to prevent against that. And even in this case, the randomness is still unbiasable. So which is a nice property as well. Of course, it's not unpredictable anymore, but it's a trade-off in the design space. So I'm just gonna try a demo. Let's see if it's working. Check. So there is some fancier demo, but we're gonna have to wait for next week to try. So I'm just gonna show you the HTTP endpoint, so you can try on the Drand Cloudflare nodes. So just a REST API. So yeah, here we have the round. So it functions. We have this round of the chain. This is a signature. So this is the actual BLS signature, which I talked to you about. And this is a previous signature from the previous round. So a beacon itself is self-verifiable. You can give this to any application. It will be able to verify it. And if you want the public key, it's going to be the root of trust. So you're going to have to verify it from multiple nodes. You can just fetch it like this. So here you get the public key, so BLS 3812381 public key, and you get the period. So it's every 30 seconds we get a new random number. We get the genesis time. So as I told you before, we get this mapping between rounds and time. So we can actually say, okay, next week is going to be this round, and we want to run the lottery on this round. And so we can use potentially smart contracts to determine, okay, I want just this one and verify this one, so etc. That's about it for me. Thank you. I'm just right in time.
Awesome, thank you. Gives just some time for some questions then. I heard someone start.
Okay, yeah.
Is that you, Bryan? Yeah, okay. Well, I have a couple questions in mind. There's time for folks to add their own questions. I saw that you answered a question or carried out a, Nicolas, before you started answering. Do you want to talk any more about that? Like back in the original reason why simply doing commit and reveal doesn't work and kicking out nodes who don't respond. Do you want to respond to that at all?
Yeah, it's not an easy answer. To be honest, I started this project 3 years ago because it looks nice and as a hobby project with pairings, it looks really cool. I wasn't expecting it grow so much now, but I think like having this approach reduce a lot the possibility of the attacker actually, because the attacker, the only thing he can do, he can try to DOS the other nodes. But he cannot do so much either by hacking the other nodes. That's the only thing he can do. If it doesn't answer, if it doesn't produce his partial signatures, then the chain stops. But I mean, assuming that there's not a threshold of honest node alive, the chain stopped. But the only thing that will happen is liveness is down. As soon as the liveness, enough threshold of honest node is back online, they will start generating randomness. And we have this notion of catch-up where we start generating randomness faster than usual to be able to catch up to the round time and making this round to time consistency back as well. So in my intuition, it just provides a stronger, let's say, robustness over time. It has this trade-off as well, but I don't want to speak too much about commit and reveal.
I had another, I love seeing your slides and discussion on this, all these extra challenges that show up when you take a research, well, I guess what started as a side project for fun, then became a big research project, and then became something to move into production. So I'm fascinated with all those stories about, what else comes out there. I was really interested in the way that you described that one of your goals is to make it so that the DRAND nodes are hidden, like you don't even know from outside that it's a DRAND node. It's almost like a steganography or blending in. You want to say more about how you do it?
Yeah, so the goal is just before, for during 1.5 years, what the League of Entropy was in production, you could access all the endpoints directly. You could contact all the DRAND nodes. We eventually said, no, this is not possible anymore. We just need to make sure that the members put it publicly where, hi, I am running this DRAND node. You can check the chain info. This is a public key of the network and so on. But you shouldn't be able to access by pinging the node. Otherwise, you're just opening yourself for DOS. In terms of challenges, one of the few things that were interesting is human operation. there's been a lot of human operation errors, and it's much more difficult than we think to say, hey, we're going to run the DKG, run this command, and even this is really, really difficult to make it right, to get the right inputs over time, and the timing, the network heterogeneity as well, the latencies, because you need to work in rounds for the DKG is really, it's much more difficult than we can think about in the first place. Yeah.
Yeah, actually, that I think you know, just to follow up on that thought, is absolutely true. One of the difficulties with DKG is it's you know, I think that has been apparent is you know, it's of course a lot simpler to make a, you know, synchronous DKG. You know, I mean, it's hard enough to make a synchronous DKG. You know, kind of where everybody or a sufficient number of people are online pretty much at the same time, but then that's a management problem, making sure, you know, enough people are online at the same time to run a synchronous protocol. It would be nice, you know, I think this, you know, some of these experiences show that it would be really nice to have a fully asynchronous DKG, but fully asynchronous DKGs are still way harder. And, you know, I don't know if, and the theory people are still working on that problem.
Here's a cool question that shows up in the Q&A. Do you have things you would say about churn, handling entering and exiting nodes, stuff like that?
I don't know
so,
who is the question. Yeah.
Could be either. Yeah, if you want to answer it, Nicolas, go ahead.
No, go ahead. Go ahead.
So I think, so it depends, first of all, it depends on what kind of churn you're talking about. Are we talking about short-term churn of, you know, nodes that are in the group, but, you know, going up and down, right? You know, becoming temporarily disconnected, but then coming back later. So, so short-term churn, okay, thank you. Yeah, so short-term churn is already totally handled. And, you know, kind of the use of BLS, threshold BLS, does a really good job at that. And this is actually one way that, that the BLS-based version makes the protocol a lot simpler and more robust than the former, you know, more scalable, but more complex tree-based, Schnorr signature-based version of this that, that RandHound and RandHerd did. But okay, so the question is long-term churn. Yeah, you know, what happens when nodes, you know, gradually need to, you need to reconfigure the group so that nodes come, you know, other nodes go, and you know, like Nicolas was saying, you preserve the group's joint public key so that clients don't have to know or care what that happens. This is where the resharing process is critical, like Nicolas was saying. Basically, the fact that you know, when nodes, you know, as long as you have a governance structure, a way to bring nodes in and out of the federation smoothly, you know, and you can run the resharing protocol, and, you know, the synchrony, you know, dependencies don't kill you. As you know, as long as you can get enough people online, you know, during, and keep them online during the resharing protocol and stuff, it'll totally handle that just fine, you know. But of course, you know, it brings these logistical difficulties, you know, challenges. You got to do that, governance and stuff like that, right? I guess that's my perspective. Any further thoughts, Nicolas?
Yeah, I think I want to join Andrew's Miller's thought on last talk that you mentioned, like in this case, we have a permission network, so we had some individuals. I was running a Drand node. I stopped running it because now it's involving a lot more operational effort. So we have monitoring in place. We have for each members, we ask that there's always a team, somebody available. So, and we can react much more smoothly. It's like not like in decentralized system where, yeah, one node is out, no problem, we can see it, but it's okay. Now we have a whole operation in place, which change the mindset of how do you run the system as well.
Okay, I think we're at the top of the hour, so we should let that be the wrap up. Thank you again, Nicolas and Bryan, for the excellent presentation.